Hi, I'm Tim Coyle, your instructor for today's lesson from Top Gun Hardware Academy. Visit us online at topgunhardware.com to see how our online training portal can help increase your skills as a hardware and software engineer. Today's pilot briefing is going to be on using formulas to calculate PCB trace impedance. Let's get started. So let's first start off why impedance matters. Good signal integrity practice is all about impedance matching. So if you look at this diagram here, what you're going to see is the source, your system, and your load. And what you want to do is you want to have everything with a matched impedance. So you want the output of your driver impedance to match the impedance of your transmission line, and that should match the impedance of your termination. So for example, if everything was 50 ohms here, and you had a 50 ohm driver with a 50 ohm trace that was into 50 ohm termination, you would have no signal reflections, and you have really good signal margin at the input of your receiver. Now this diagram on the far right, I'm showing a lattice diagram, and what this is a way to calculate what the reflection looks like going from the source to the load as the signal goes back and forth. Think of a reflection as a wave in a pool, and it goes down from one end of the pool to the other, and then energy reflects back of the wave and it goes back to the beginning, and it keeps bouncing back and forth until it evens out. And you can see that on the bottom diagram here of voltage versus time. And if you look at your source and versus your load, you can see how the reflections are different as the signal energy goes back and forth. But really, impedance matters because this is how your reflections are contained or not contained. The impedance of a trace can be calculated using equations. The equations have been developed and refined throughout industry to numerically calculate impedance of PCB traces based upon the dielectric material and trace geometry. So at the bottom of this slide, you can see an example microstrip impedance equation. And if you look at this formula, it's really based on the trace geometry, for example, the width of the trace, the thickness of it, and the height of the dielectric constant, and also the dielectric constant value. For example, this could be a laminate made of FR4. However, these equations are partial solutions and valid only for a limited range of parameters. Some equations are based upon measurement fitting data. So these equations are useful to calculate PCB trace impedance, but there are accuracy issues. So let's look at this next graph. This is a microstrip trace width comparison. So what I'm showing you here is this blue graph. This blue line is the calculated impedance using the formula, and the red line is the calculated impedance using a 2D field solver. So you can see that under some situations, for example, when the trace width is say 4 mils, both the calculated formula and the field solver are very close to be about around 60 ohms. They're a couple ohms off. So these impedance equation formulas can be accurate under certain conditions, but they're always going to be a couple of ohms off. Now, plus or minus 5 ohms might not be a big issue when you're doing the beginning part of your stack-up planning. But when you go to final production, based upon your accuracy and your yield control, you're going to want to use a field solver to make sure that the values that you're using are giving you accurate results. So when calculating the trace impedance, analytical equations work good for approximations and doing quick what-if analysis. You need to consider the PCB fabrication variations at some point in your PCB stack-up planning. The PCB fab shop will guarantee your impedance usually to plus or minus 10%, or you can pay more for tighter tolerances, say plus or minus 5%. Depending on your tolerances and depending on the PCB fabricator you're using and the process you're using, the PCB fabricator will change the trace width, the height, the thickness of your laminates in order to reach your target impedance. The dielectric constant is set by the laminate material choice though. And there's other considerations not seen with the impedance equations. For example, crosstalk and loss, both skin effect and dielectric loss. So using impedance equations, you're not going to see the full impact of the overall signal integrity of the trace that you're using, but you will see the impedance. So the final PCB characteristics impedance should always be verified by a field solver. don't rely just on the PCB fabrication shop to tell you what the impedance is of your stack-up design. Remember, you own the signal integrity of your design at the end of the day. So really, I think this is how you should use both equations and a field solver to do the impedance for your PCB stack-up planning. So on the left is our W solver tool, which has both the calculations and also a tie-in to an open source 2D field solver. So the way I recommend it is to use equations in the beginning of your PCB stack-up to quickly calculate your target impedance. So for example, in this example I'm showing here, for a microstrip trace, you're trying to get to 50 ohms, you're setting your trace width, you're setting your dielectric height based on the laminate material of your choice, you're using the dielectric constant of that. And then you can use these built-in equations to quickly analyze and see as you change your trace width, you change your trace height, or you change your dielectric height, or you choose a different laminate that has a slightly different dielectric constant, what you're going to get for a trace impedance. So what you want to do is, based on your stack up, to see how close you are to your target impedance, say 50 ohms or 60 ohms or whatever it is that you're using. And once you've done that, at that point, then you can go and use a 2D field solver to get a final impedance value. And this is normally what your PCB fabrication vendor should do, is once you're done with your stack up and you give that to them, you know, and part of their fabrication process is they'll calculate and tell you what the characteristic impedance of your trace is based on their process. But you don't want to wait until you get to that point and have your PCB fabrication shop come back and say, oh, well, you know, you wanted 50 ohms, but our process, it's really going to be 65 ohms. So you should be within a couple ohms of your PCB fab vendor. And if you're not, then you need to work with your vendor to figure out why. So this is my recommended way of how to deal with PCB stack-up impedance. So what I'm showing you here is our W solver tool, which you get for free when you sign up at Top Gun Hardware Academy for either of our monthly or yearly subscription, and you can also purchase it through a one-time download purchase as well. So the way W solver works is this interface, and I'll show you the microstrip interface, is it uses calculated formulas that we went over in the previous slides. And so for example, you can see here it starts with some default values for a stack up, and at the bottom it'll calculate the impedance and also the delay. Now you can use these sliders to change this around and see how your impedance changes when you change any of these parameters, whether it be the trace width or the dielectric height. And you can also see that up here under parameter sweep, you can put in values here. For example, we can sweep the trace width from 5 to 10 mils by 1 mil steps, and this uses the calculation, and I'll pull the graph into the screen here. And what this does is it plots the trace width going from 5 to 9 mils by 1 mil steps, and it plots the impedance. And this is using the calculated formulas. And so this way you can quickly see what happens. For example, if you're trying to get to say 60 ohms, and let's say you started at 5 mil trace width, well, that's actually more at 67 ohms. So here you realize that, well, I need to go up to almost 7 mil trace width, or actually 6.25 in order to get the 60 ohm target impedance. So you can see with these different sweeps that you can go through and figure out what you want your impedance to be pretty quickly. And there's also a link to a field solver so that you can run this. For example, create a file, and then we're going to run the quick simulation. So this is TNT's an open source 2D field solver that you can download and bundle with this. And then we can view the result. And if we load the file, microstrip result, here you can see that it's calculating the impedance of 84 ohms. And you see in this example, we've got, probably not a realistic example of having a 3 mil trace width, with a dielectric height of 5 mils, there'd be 80 ohms for single-ended. But you can see that this is a good example of showing you how you can get a slightly different result between your field solver versus the actual calculated impedance. Normally it's a couple ohms. And this is why you always want to use the field solver, because this is going to give you the most accurate result. So this was just an example of how to use both the calculated formulas and the calculated field solver result to do your PCB stack-up planning.